My name is Marty Itzkowitz. I'm the project lead for the Oracle Solaris Studio Performance Tools. And my colleague Scott Oakes and I are going to talk today on how to improve the performance of your Java application. I'm going to give the first half hour or 35 minutes of the talk on profiling and Java profiling, and then Scott will talk about a specific example of how the tools improve performance on a large app. So, here's what I'm going to talk about. First, about why performance matters, why you care about it, and what to do about it. Then I'll go through some low-hanging fruit, a really simple example of two performance problems. Then I'll talk in some detail about Java profiling and both the model that the user has and the model that the tools have, and talk about profiling enterprise class applications, and then Scott will talk about profiling Fusion Middleware. So, why do you care about performance? Performance matters because faster code means greater productivity, which means lower cost. It also means faster results, which means lower cost. My favorite reason of caring about performance is that it's interesting and surprising. And the reason for that is that most programmers have some idea, some mental model of how the program is going to behave, and that's what they code to. If there is a disconnect between that model and how the code they wrote actually behaves, that often can lead to a performance problem. And you can do something about performance problems. With our tools, it's very easy to identify where the problems are and how to fix them. We do simple runs, fully automated runs. When you care about performance, you care about what criteria. The obvious one is that it just takes too long. Either a transaction takes too long, or a model that you're running takes too long, or something. It also could respond too slowly. If you're dealing with a transaction system, you may find there's too much latency between the time the user placed the order and the time they got a confirmation. It may mean that your server can't handle the required load. It's also true that it may consume too many resources. That is, if you're running on a system where you may have a cabal of interacting processes to accomplish some business objective, if one process takes too many resources on the machine, all the others will be slowed down by that. You always have to look, when you find a performance problem, is it worth fixing? What's the aggregate cost of engineering the fix versus the aggregate cost of the problem? That is, if you have a program you've developed for a special purpose, you run it once, you fix it a little bit, you run it again. It still seems slow, but you're not interested in running it anymore. There's no point tuning it. On the other hand, you may want to shave milliseconds or even microseconds off the time to process a transaction so you can handle a larger load with less hardware. One interesting thing that I've observed is that most untuned codes have what I like to call low-hanging fruit. That is some real silly way of writing something that is very expensive and needlessly so. And even some tuned codes can have low-hanging fruit. Depends on how you look. So once you decide, once you decide there's a problem, you have to find it and you have to triage it. The key to being able to do that is to have repeatable performance runs. That is, I can run the same thing over and over again, and I know how much time it takes, and it's repeatable. It takes about the same amount of time every time. Once you do that, you can monitor such a run to get the performance data. It's important when you're tuning a code to use realistic data and scale. It's not much point tuning a code to handle a list of 50 items when in production you'll handle a list of 50,000 items. You can also, just to decide whether or not there's a problem, you can use virtually anything. You can look up at the clock on the wall. You can use bin time. You can use a stopwatch. Anything will tell you if this is taking longer than you think it should. It turns out that most problems arise in terms of scaling. That is, almost any code that you run has some intrinsic scale factor, the number of items in the database, the number of lines of code, etc. And it's important to understand, how does the performance of your application change with that scale factor? Does it go as order n, or as log n, or n squared, or n to a higher power, or the exponent of n? The higher, depending on what that is, it tells you where you have to look and how important it is to fix it. If there is a problem, you need to get detailed data in order to be able to understand it and fix it. So we're talking about the Oracle Solaris Studio Performance Analyzer. It has a very simple user model. It provides lots of different kinds of data so you can look at many different kinds of problems. Some of the data is statistical in nature. That is, you're doing a statistical profile of where the program is spending its time. Statistics really work. Some data, tracing data, for example, is exact, so you know exactly what happened. The trade-off is usually that tracing data will slow down your application and produce large data volumes, whereas statistical data can be tuned to get reasonable data volume and relatively low intrusion into the running of the program. Our tools have a uniform interface to all the data. There's a parameter that you give to one command that says what kind of data you want, or set of parameters. And once you've done that, when you look at the data you've recorded, the tools understand what data is there and know what to show you. The performance analyzer, which is what we're talking about here, is the application performance profiler in Oracle Solaris Studio. It works for production codes and production runs. That means you don't have to recompile or rebuild your application. It works well on runs that run from tens of seconds to hours. We can deal with many CPUs, many processes, many threads. We have one example of building the JVM where we profiled the make command, which had over 17,000 processes in that run, and we just collected data on everything. We deal with real production codes, which means you can use fully optimized and parallelized applications, and we can profile them. When you're profiling Java, of course, Java Hotspot is enabled, and we deal with that perfectly reasonably. The tools in general have minimal dilation and distortion. Dilation is when you do a measurement and it takes longer. Distortion is where the relative cost of different parts of your program will change. We have relatively low for both, order 5%, somewhat higher, perhaps as high as 10% for Java applications. And when I talk about Java profiling in detail, you'll see why. The codes that we have support codes compiled with the Oracle Solaris Studio compilers or the GNU compilers for native code, and with various JVMs from the Oracle Java development releases. And the tools support both Oracle Solaris and various flavors of Linux. The objective that we had in designing these tools was to make things as simple as possible. And that means show the data that we've recorded in the user's model of what they wrote the code to do. That means showing Java threads, showing OpenMP, MPI, all of that complexity. However, you can make things as simple as possible, but no simpler. There is some complexity that you really have to take into account. The compiler for native code can do extraordinarily complex transformations on the code so that the generated assembler kind of bears no relationship to what you wrote in your source, but it's important that the tools feed the data back to annotate your code, not the code as transformed by the compiler. We also, with the Oracle Solaris Studio native compilers, we have a feature called compiler commentary, where the compiler puts information about what it discovered in processing and optimizing your code into the executable. We can then read it and display it, and you'll see examples of that later. For Java programs, it's important to show what the JVM did. That means show both interpreted methods and hotspot compiled methods, to show the garbage collector activity or the hotspot compiler activity. Basically, the tools run in 3 simple steps. The first step, build your target. I use make a.out as doing it. The second step is to collect the data, and that's very easy. Instead of running a.out with its arguments, you run collect a.out with its arguments. There are lots of flags you can put between the collect and the a.out to specify different kinds of data, but that command will work and collect what we call a default experiment. The third step is to look at the data, and you can do that either in a GUI or in text from a command called erprint. So once you're looking at performance, what do you really want to know? You want to know primarily what you can change in your code to improve its performance. You want to know what resources are being used by the code, memory bandwidth, disk transfers, etc. Where in the program they're being used, and often you care how the program got to the place where that's being used. It doesn't help you to know that you're spending all your time, let's say, in a matrix multiply routine, if you don't know that it's coming from the matrix multiplies of 100 by 100 matrices and not the 2 by 2 matrices. You have to understand the path to the hotspot. The objective we had in developing these tools was to minimize the number of steps you have to take to get to the aha point, the point at which you basically slap your head and say, what idiot wrote that? And then you know how to fix it. We have several technologies. We can do clock profiling of call stacks. That is, as a profiling clock ticks, for every thread we record the call stack at every tick. You can do the same thing for hardware counters, which gets you more detailed information about instructions, about floating point instructions, about memory operations, and so forth. Or for some things, you can trace events. You can trace memory allocation and deallocation events. You can trace synchronization events. The biggest wins in performance tuning, excuse me, often come not from understanding the detailed code and the detailed sequence, but from large-scale algorithm changes. That is, people who write compilers care very much that the generated code not have as much as one extra instruction in it. And they will look for 1% on spec. Most application developers will quit at the 10% point, not the 1% point. And the big wins come from changing the strategy you're using to do the computation. And I'll show you that in a bit later. So now I'm going to talk about low-hanging fruit. I have this silly program I wrote, which was called low fruit in C++ and is JLow fruit in Java. And it does two things. One is it initializes some tables. And there are two versions of it, a good version and a bad version. The two are shown. You can note that the inclusive CPU time, the second column, is substantially higher in the bad initialization than the good initialization. And the other two that I'll talk about later are the good insert and bad insert, which are bracketed. So what you're seeing here is the function list. That is, I recorded a default experiment just like I had described. I said collect JLow fruit, and what came up is this data. That shows the functions in the program and how much time was attributed to each. First column is exclusive time, that is time executing in that function. The second column is inclusive time, which is time in that function and everything that it calls. So here's an example. There's a factor of, 6 or 7 between the good and the bad. If you look at the bad initialization, there's a call to a static initialization routine inside a loop. And it's spending most of its time there. If you look at the good version, it's outside the loop and spends much less time. Now, you might think this example is really dumb. No one would write that. But in fact, it's based on a real problem in a code I wrote many years ago. And the problem was not that there was a simple call to initialize explicitly in the code. The problem was picking which API to use from some toolkit and understanding the implications of that API. In this case, I was writing a program whose output was a list of loops, and next to each loop was an icon saying whether it was serial or parallel, and if it was serial, whether it was serial because the compiler thought it best, or because it couldn't be parallelized for one reason, etc. Worked fine for 10 loops. I tried it on 900 loops, and it took forever. Clearly something was broken. There were two APIs I could pick to use. One added an icon to an entry in a table. The other relied on the user to build a vector of icons and then add all the icons to the table at once. It turns out that if you adding the icons causes a recompute of the height, because the icon might be taller than the text in the line, and you have to adjust it so that all the lines are the same height. So if you add the icons one at a time, it will scan it to find out the height of the whole list. And if you do that for n icons, you're scanning an entry of n lists n times, you have an n squared algorithm. If, on the other hand, you build a vector of icons and add it to the entire table at once, you have an order n algorithm. Actually, it's an order of 2n because you have one pass of n to construct the array, the second pass of n to do one recomputation for all the icon heights. And here's an example. For a list of about 1,000 loops, API 1 took 30 minutes, API 2 took 30 seconds. And that's the kind of benefits you can get. This is the kind of low-hanging fruit that you'll often see in real codes. So now let me look at the second one. The second one's a simple task. You have to search some list of something. In this case, I'm building a list of entries, and in the good insert, I will do a binary search to find the right place to put it. In the bad insert, I will do a linear search. And again, the tools show you the difference in performance in good insert and bad insert. You can see is enormous, a factor of 3 almost. And if you look at the source, in the bad insert, in the linear search, you can see all the time is being spent in repeated search through this table to find out what the right position is. If, on the other hand, you look at the source for the binary search, which is more complicated, more source code, and so forth, there's virtually no time spent in the search. And that's, again, simple example where changing from a linear algorithm to a binary search algorithm gave you an enormous improvement in performance. So I've talked about why you care about performance and the low-hanging fruit example, and now I'm going to talk in some detail about what we do to profile Java applications. You might think that the JVM is just a C++ program, so what's the problem here? Should work on any program. Well, it turns out the JVM is not quite as simple as it seems. It has lots of peculiarities. For one thing, it dynamically creates the bytecode interpreter in its own data space. It allows calls to JNI and back to get from Java to native and back again. And when the hotspot compiler comes in, it will generate machine code for a Java method and put it into the target's data space, not instruction space. Typically, the JVM has many threads. There are half a dozen or a dozen of what I would call system threads that are always there. They don't do very much, but when they're needed, like garbage collector, which may have many threads, or the hotspot compiler, which may have several threads. There are also two call stacks that are relevant when you talk about profiling a Java program. If you stop it at any point and try and unwind the stack, you can do a Java stack, which tells you where in the context of the Java program the program is, or you can do a native stack, which tells you what's actually going on in the machine instructions. And sometimes you really have to do a combination of both. And what we do is, well, I'll talk about what we do later. Another complexity of Java profiling is that memory management is all done through a garbage collector, and that optimization of the code is done by the hotspot compiler, and it may actually take a method and compile it more than once. But the same performance questions you have about where's the program spending its time, where's it using resources, how to get there, those are the same questions, but they're complicated by the Java peculiarities. So to cope with those peculiarities, our tools support 3 ways of looking at profile data on a Java program. There's a user mode, which really corresponds to what the user thought he or she wrote. In the user mode, we don't count what's going on in non-user threads. We merge the time spent in interpreted and hotspot compiled versions of the same program, of the same routine rather, so you see the time in that routine, not separated into 2 different times. And when you ask to see disassembly, one of the features in our interface, we will show you bytecode annotated with performance data. We also have an expert mode which is for people who are writing or primarily interested in Java, but have a little more sophistication, and so they're interested in garbage collection issues and hotspot compilation issues. For that, we do count the non-user Java threads, because GC and hotspot are non-user Java. We, again, will merge interpreted and compiled versions of the same user method. And the disassembly will show you either annotated bytecode for Java code or annotated machine code for the parts that are not Java. We also have machine mode, which will show all threads. It will show the interpreter, not the methods being interpreted, although when you're executing hotspot compiled methods, you will see those methods. And the disassembly will always show annotated machine code. So here's an example of a program that I wrote. Here's a simple default example. The application is a Java code that has calls to a C++ shared object. So here's the call tree of the program. You can see that highlighted line, the selected one, comes from a shared object, libcloop.so, that tells you it's in native code, not in Java code. But the routine above it that calls it is from Java code. So the highlighted function actually is called from Java and calls back into Java, and that's what you're seeing there. If you look at the timeline for this program, it shows you basically the sampled call stacks as a function of the real time. You can zoom in on that and you can actually see that what look like continuous bars are tick marks that are separated by about 10 milliseconds. In this case, we're in user mode, so only the user Java thread is shown. That's thread 2 in this example. And the Java does a lot of funny things, so it's often hard to infer which thread number corresponds to what's going on. Another complexity of Java is that some implementations will exec themselves. So if you profile Java, the process that you really want to profile is not the one that you first launched, but the one that is exec'd after that, and we just deal with all of that seamlessly. As I said, we have other modes, so I can switch to expert mode, and now suddenly I see, in addition to the user thread, this is zoomed in, which is why you can see the separation. You can see there are other threads. Thread 3 is the garbage collector thread, and threads 7 and 8 are the hotspot compiler. In this case, you can see the non-green events there. The green events, rather, are when profile tick happened, but the process was not running on the CPU, like it's waiting. And in fact, that last thread spends most of its time waiting. But there's one example in thread 3 where there is a spike of activity, and you can see from the call stack, this is obviously part of the garbage collector. So I've selected that event, and I know it's part of the garbage collector. What I want to find out is what's happening. So I use the button to move up to the corresponding time on the Java user thread, and I see it's in this Java function called routine.memlock. And it's that function whose heavy execution is what's triggering garbage collection. If you look at the source, it's really pretty easy to see why. The source allocates a large array of this my object, and it just does it in a loop, but it keeps overwriting the pointer. So it's basically creating garbage as fast as it can, and that's why you see a spike in the GC activity at that point. So I've talked about the general understanding of Java codes and Java profiling, and now I'm going to talk a little bit about the issues that arise when you're dealing not with a simple Java code, but with enterprise class applications. Enterprise class applications can be very complex. You may have many processes all interacting, and it may each of those may have many threads. It may run for a long time. Typically, you really want to track everything that's going on so you can see what's happening. And also what's typical of these applications is they may take 45 minutes to reach equilibrium. So you don't care what's happening as the process starts, but you do want to get what in urology would be called a clean midstream sample for understanding what's going on in your program. Another issue in these enterprise class applications are performance issues concerning multiple threads.
Thank you.
To do that, performance issues on multithreads usually have to do with lock contention. And there's a difference between locking a large part of memory, a global lock, or a local lock. And in fact, the whole trick in any lock programming is to get the scope right. If you get it too big, you may be blocking things that don't need to be blocked. If you get it too fine, you may be spending an awful lot of time acquiring and releasing a lock that is virtually never contended for. So choosing the scope of a lock is a very important performance issue. Another issue is load imbalance. What really matters is useful work being done, not necessarily CPU usage. In some programming models, when something is waiting for something, it will do a busy wait. It'll spin waiting for a lock to be released. That uses CPU time but does no useful work. Another issue about these enterprise class applications is that they're often extraordinarily complex to launch. They're launched by scripts, and one of the things you can do is you can look at the various things that get launched by that and just stick an environment variable in front of each command that launches a process you may care about. If you do that, you then, if you run the script without setting that environment variable, it runs normally. But you can set that environment variable to, let's say, the collect command that you want to use for that process, and then you'll collect data at the same time you run it without any other change. Another thing that you can do is we have an argument you can give to collect that will control when you collect data and when you don't. So if you invoke it with, let's say, -y user, that means don't collect data until sig user is sent to this process. And every time you send sig user after that, it will toggle data collection on and off. Another thing that you can do is you can mark events. So for example, you may set a signal that will put a marker in your data, and you can send that signal, then you do one particular operation, then you send it again. What happened between those two signals, which is very easy to filter out, will show you what that particular operation did. You can also put API calls for markers in your code. Those calls are ignored if no data is being collected, and they have the effect that you want if data is being collected. Once you've got this, you want to filter to drill down on problems. You may care based. You may want to filter only if a particular function is in the stack or a particular set of functions. You may filter on a subset of threads or processes. You may only care what's happening on one particular CPU. You may filter to only look what's happening between marked events. And all those are important in understanding these applications. So I'm going to go through a couple of simple or not so simple examples. One is a profile of the Oracle database. This was collected during the TPC-H power test. It was script launched using this flag to turn data on and off. And the queries are launched by another script. It sends the signal to enable data collection. It runs the query. It sends the signal to turn it down again. That means that every experiment has start and stop markers for every query. In this case, it was run on a 128 CPU machine, which ran 906 processes. Many of those processes are ephemeral, and they actually don't even get clock ticks. They don't even get even one profile tick. But 256 of them do significant work. So here's an example of the data from a 40-minute run, 49,000 seconds of execution time. Here's a picture of the data sorted by CPU number, and you can see that some of the CPUs are actually used substantially less than the others. And you can also look at per process. I've set it up to look at the processes of that Oracle run, and there are many of them. I can filter to look at only the top 5 of it, and then when I look at the data, I see what's being done by only those 5 processes. So I'll talk one more example, SPECjEnterprise. This is a benchmark that emulates an automobile manufacturer. It stresses servers, the JVM, CPUs, etc. It runs on a 128 CPU machine and does 282 threads. Basically, data collection was enabled in this run for 2 300-second steps. And the data that you see only covers those intervals. So here you can see where the data was being collected. You have profile events, otherwise you don't, and they're all in WebLogic. You can see that most of the time in this case is spent in the WebLogic middleware. And that's the nature of the benchmark. And the last example I'll talk about is the Oracle Service-Oriented Architecture Suite. Again, based on Fusion Middleware and WebLogic, handles many complex events, has a performance requirement of near real-time performance. And again, this was run on a 64 CPU machine using 166 threads. And in one run, we collected both clock and cache miss profiles. So you can see there are two main paths here that are highlighted, and I infer these from the names, of course. One is the user WebLogic thread, and the other is the compile broker. So a fair amount of time was spent deciding whether or not to compile the hotspot compiler and actually doing it. And again, you can filter. I can say I only care about what happens when that one function is in the stack. So I'll throw out all the other stuff. So I'll throw out all this stuff about Java, the compile broker, GC, etc. Okay, I've described basically what the tools do and how they work, how they handle Java programming, went through a low-fruit example, and went through some examples of fairly complex code. And now I'll turn it over to my colleague, who will do the rest of it and talk about profiling a real application.
Thanks, Marty. So I work in the performance, scalability, and reliability group at Oracle, and I'm going to give a case study on how we use the collector and analyzer to profile one of our Fusion middleware applications. So I don't know, probably many of you are not familiar with Fusion middleware, so I'll just talk a little bit about it, and sort of the important takeaway about it is that we're talking about very complex, very large programs here. So in particular, if you know the Fusion application suite, we're profiling the BPEL, or Business Process Execution Language, part of it, which is a component of SOA, and that's what it does. The point about this particular application, and really a lot of the Fusion middleware applications, is it's very, very large. So all that stuff that Marty talked about, that we can scale to processes, we can scale across CPUs, really plays out here. We're talking an application that has around probably 40,000 classes. And in this particular example, we didn't actually use it, but we regularly scale this application and profile it with a 55 gigabyte or larger heap. So the scale that this tool that we can handle with these tools is quite large indeed. For this particular example, we chose to run on a Solaris Spark T4 system. So it has 456. There are 456 software threads. There's 256 hardware threads in the thing. For this particular example, we have only an 18 gigabyte Java heap. Another thing about this application show just the scale that the tools can handle. We have Java thread call stacks in this application that are hundreds deep. I mean, it's a big application. So when we first bring up, so after we've done the collection and we've done the experiment, and we bring up the analyzer, so this is what we see. So there's a couple of interesting things to look at on this slide, and I'm actually going to focus on the left side. Forget the red circle for a minute, which is where I'm going. But typically, when you'd bring up a profiler, you'd look at the left side. You'd say, okay, where's my application spending a lot of time? And if you notice, so if you notice under the user CPU columns, it's not really spending a lot of time anywhere, right? The top one here, which is JVM system, is spending 1% of time in CPU. There's something else that's spending 0.64% of time in CPU. This application doesn't necessarily have the low-hanging fruit that Marty talked about, right? We've tuned it a lot. We've done hopefully a good job at tuning it. You're not going to say, oh look, there's something that's taking 40% of my time. That's where I know where I have to go profile. One of the things that we can do with collector and analyzer, though, is it gives a level of visibility outside of a normal call stack and a normal call tree. And so that's the examples that we're going to focus on in this part. And so the first thing that we did notice actually after the fact that the call tree profile was flat and wasn't necessarily going to help us is that it seems like we're spending a lot of time in user lock. So we're going to use the features of the analyzer that show us locking behavior, which is not something that you necessarily see in a typical profiler, and see how that can help us find out where we can improve our performance. So the first thing that we're going to do then is, so we're going to select the user lock metric. We're going to sort our left column by user lock method. We see that the top thing that we're spending time there is, we see that we're spending 40% of our time when we highlight the JVM system lock. We're spending almost 46% of our time in JVM system. So that's interesting, but what does that tell us? So this is one of the times where, as Marty explained, you need to dig a little deeper. Your behavior is not necessarily in your user code. We need to actually switch view modes to see what we can see that's a little bit different. So we're going to switch. Now we switch to the view mode. It's the view mode that the menu choice next to where it says view mode. We switched from user to machine. Now we can see what actually is spending time in our JVM lock, and we see that everything's calling LWP condition weight. It's a normal sort of Unix style condition variable that we might see, and now we can switch to the callees tab and do sort of regular profiling to see who's calling that lock and look at a normal sort of call tree that will tell us who's using that lock and what we're used to seeing there. And it will come as probably no surprise that what's doing all of this locking is actually the garbage collector, because of course all Java performance problems are because of the garbage collector, right? We all know that. So this tells us that one of the first things that we might want to look at is perhaps tuning our garbage collector, reducing the amount of time we're in garbage collector. That's what's going to be the sort of first order for how we can solve our issues with the user locks. But let's dive a little bit deeper, right? Because although we had 40% of our user lock code there, we still have a significant amount of user lock time that we're spending in other branches. So we're going to use the filtering mechanism that Marty talked about and to look at the rest of that. So in this case, we've gone into we've gone into the call tree. We've highlighted the GC task. We know how to deal with GC. We know how to tune GC. That's not necessarily going to help us here. So we're actually going to filter out the GC. We're going to include only stacks that don't contain the calls into GC. And now we're going to see what's taking up the rest of our user lock time aside from GC. That is the user lock time that we're actually going to be able to do something about. That's actually in our application code. Okay, once we've done that, we're going to get a regular sort of callee tree. And at this point, I'm going to assume that most of you are familiar with profiling tools. You know what a callee stack looks like. You know how to say, oh, okay, this is what's calling my locks. I should go look at that code. I should figure out how to make it call fewer locks. At that point, it's sort of similar to what you'd use from other profiling tools. The point is we were able to get to this point in a sort of unusual way because it wasn't CPU time that we were looking at. But there's more than one way to skin a cat. And so one of the other things that the collector analyzer provides is this visibility into the timeline of the thread stacks that Marty talked about. So again, this is a level of visibility into your application that you're not necessarily going to see from a traditional profiler. It turns out to be very, 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 very useful with the collector analyzer. So if I bring up the time, if I still have my data filtered and I bring up the timeline for this particular operation, you'll see I see the timeline is the part of the window shown on the left here. You'll see that I have a bunch of stacks. And most of the stacks are busy most of the time, right? There's the colored bars are where they're doing things. And they're busy, and there's a little gap, and there's busy, and there's a little gap, and that's what we normally see. You can guess that those little gaps, since they're periodic and regular and affect all the threads, are GC. But what about the other gap for those other big three, those three threads in the middle, right? Those three threads in the middle have a big gap in them where they weren't doing anything. That's not GC. We know it's not GC for a number of reasons. We filtered out GC in the first place, but also we know it's not GC because it's not affecting all the threads, and it's really much too long a time period to be GC. So here's a point where we've discovered that the threads are blocked. They're not able to actually do anything. So they're particularly blocked, and we can now use this part of the timeline tool to go in and see what exactly is the code that's holding the lock, what exactly is preventing those threads from actually executing, what sort of thing are they blocked on. And so we're going to go and do that. We're going to find out that the particular call they're blocked on is this interceptor chain manager, and now we know where to go look in our code. We're going to go fix the lock associated with the interceptor chain manager. We actually did that, getting rid of this bottleneck in our synchronization, getting rid of that hot lock, improved our throughput response time by about 5%. And we were pretty happy about that because, as I mentioned, this is a pretty well-tuned application. We're pretty happy if we can get 5% improvements at this point in the life cycle of the product. Okay, so what happens after we fix the code? So after we fix the code, we want to sort of make some verification that we've done something well, right? We have the ultimate verification because we ran the code and it ran 5% faster and we're very happy. But it's always nice to sort of go in and check to make sure that you've done the right thing and check to make sure that what you've seen happen. So here we use another feature of the analyzer tool where we can actually compare two runs of the same code. So the sort of darker green column on the left of this slide is where we loaded our initial experiment. And the lighter green code is where we've changed the code now and we've rerun the test. And now we've loaded that into the analyzer tool. And now we're actually comparing the two results. And happily, we can see that in the dark green code, we were spending 12% of our time on this interceptor chain manager lock. Now we're not spending any time waiting for that particular lock. So in fact, we did fix the code correctly. That's why we got the benefit. Another really nice thing about this comparison tool is that, so this is all sort of graphically based, and that's nice if we're sitting in front of our computer. But another nice thing about this comparison tool, and really all the tools, is that they have another mode where they work, which is through a command line. So this print command line gives you the same data that you get out of the profiler, but it gets it all textual based. So here we've done the same thing. We've used print and we've loaded the two experiments and we've dumped out the data and we can do the comparison and we can sort it visually here. The nice thing about that though is, and actually one of my colleagues asked me about this before the meeting, if you wanted to script your performance, if you wanted to script your analysis of your performance this way, you can do it this way, right? Because we can script print, because it's a script, because it's all textual based, I can make this part of my regular performance testing. I can, I can use collector, do a run during my regular performance tuning, maybe using the -y flag and that Marty talked about, turn it on only during one particular part after I've done my performance measurements. Then I turn on profiling, then I gather a profile. Then I use print, then I dump this out. Then I write my script to at least dump out what the hot methods are or dump out any comparison tools or whatever. So this is fully integratable into a nice sort of scripting-based test system, and we, it's something that in my group we're actually starting to do just a little bit of, but the power here is actually fairly significant, I think. Okay, so that's it for the case study. I'll turn it over to Marty for some closing words, and then we'll take some questions.
I don't really have much closing words to say. That's kind of what the Oracle Solaris Studio looks like, and there's a download address for where you can get it. The tools are available free, although it's good to buy a support contract for them. Support is not free. And I guess either of us will take questions. Any questions? Yes?
What would you say are the main differences between this product and the intelligence application?
Well, for one thing, we can deal with getting Java call stacks from interpreted code. For another, we can show annotated bytecode and annotated source lines, as well as showing some details inside the JVM, which I don't know that they can do. One thing they do very nicely is they have these high-level tasks that you can select. So understanding long latency operations, for example. And it will tell you the combination of hardware counters to use to profile to understand that. And I think that's pretty nice. I don't know how they deal with large scale and large complex applications. You know, if you've got 16 Oracle processes running plus all the middleware processes, et cetera, I don't know how well they can deal with that situation. Yes?
Is there any sort of performance drain or analyzing, say, for example, a production problem while in production?
Well, there is a cost. It will slow down the application about 5%. It may interfere with disk I/O depending on how sensitive you are to disk bandwidth. We put a lot of work in tuning the way we do I/O inside our data collection. In particular, we open a file and allocate a large chunk of it in memory map it, then close the file. So all the actual I/O is done by writing to memory mapped areas in the application.
But in comparison to, say, for example, Fusion VM?
I don't know the answer for that, but we believe that our overhead is quite low. As I said, 5% perhaps. Yeah.
CPUs today have a lot of different hardware counters.
Excuse me?
CPUs today have a lot of different hardware counters.
Yes, hundreds.
Yeah, can you select them or
Yes, you can select any. We have a set of what we call well-known counters that we try to make available on every machine, no matter what their real counter is concerned. For example, we have a cycles counter, which translates to one thing on Sandy Bridge and a different thing on Nehalem and a different thing on T4, etc. Same thing is true with some of the memory counters. But any counter that is supported by the chip, we can profile on. You have to be careful. There are some counters on the chip that are not useful for profiling because they don't count events generated by the code that's running at the time. You know, for example, cache invalidates coming from something on another CPU. You don't want to profile on that because it'll interrupt your CPU, which won't tell you anything at all about where that came from. Yes?
What do you guys use for memory profiling?
Memory as in heap profiling? Understanding the heap? There are other tools and techniques inside the JVM. We don't actually do it on Java code. We do it for native code.
Just does the native code?
Oh yeah, it's the same tool. It does native code, Java code, mixed native and Java. You can profile scripts and everything they call. You can profile OpenMP in C++ or Fortran. You can profile MPI in C, C++, and Fortran, etc. We're trying to cover all the typical user models. Yes? Uh-huh. I'm not sure what you mean. When you run a collect command, it will create an experiment in addition to running your command. You can look at that experiment at any time, anywhere. So I don't think, does that answer your question?
Well, I'm thinking the approach I would, so if I was doing an automated performance,
Uh-huh.
like you're talking about, I would have to have a program that takes the output of VR prints and then
Uh-huh.
waits for values. I want to see, how many threads are running, what they were doing, that kind of thing. Is there a direct API? Can I write a program to call in?
We do not support other people reading our experiments. You can dump them out with our tool, and there are people who have dumped out the raw data and built a profiling GUI on top of that raw data. Well, no, they didn't reverse engineer it. We document the command to dump out the raw data, but it's pretty tricky because we use a fairly intricate way of storing data. For example, a profile event has a 64-bit integer call stack ID. The call stacks are actually written with a matching ID to a different file. So you have to get all that stuff tied together correctly.
So perhaps, when you saw ER10, everything in ER10 takes an argument for all the tabs that you saw. So you can say ER10 that function and you will function this. Maybe that's what they're looking for, right? That you can dump that function this and compare it.
Right. In fact, we do that all the time. We run hundreds of tests on dozens of machines every night. And in those tests, we run codes that measure their own behavior. And we run them under our profiler, and we use scripts to compare the file that the program wrote saying how much time it spent and the ER print output that says how much time was spent, and make sure that it's close enough. That is, that the errors, that the differences between what the program says and what we say are really statistical fluctuations or understood in a particular way. Any other questions? Yes. You mean the data object rather than code? No, we don't support that. Right. Well, usually you can tell from the method which object, or are you talking about which instance of the object it matters? Yeah, we don't support that. The profiling, the statistical profiling doesn't get the pointers into the data space that say what the object is. We only get the instruction sequences. Any other questions? Yeah. Yes. No. Basically all the functionality is supported on Linux to the extent that the Linux kernel is functional. The wonderful example that Scott gave was done on Solaris because Solaris does profiling based on what they call microstates. So whether the program is in user mode or system mode or waiting for a lock or waiting for a data page or a text page and so forth, we get all the profile ticks. They don't get delivered until the process goes back on CPU, but we get an array of all those ticks. So we can profile based on time spent waiting for a lock. On Linux, you can't do that because the Linux kernel only knows about CPU time. Any other questions? Yeah. Yes. Well, not quite automatic. You have to give it a flag to say you want to follow everything. And I believe you can tell it to do that or tell it not to follow anything at all. By default, we follow everything, which turns out to be crucial for Java because it forks and execs in strange ways. And usually only one of the processes is interesting. Okay? Thank you.